Okay, so now that you've worked with linear inequalities, we are going to move into 5.1, so from the work textbook, which is looking at solving quadratic inequalities with one variable. So key difference being we're going to be dealing with x squared instead of just x, but we are still going to be dealing with just one variable, so just x. No y's, no anything else. We're not having two variables in these equations, just one. Why is this relevant? Because we still need to think of it as on a number line, a single dimension. So we're not plotting graphs of quadratics, although we're going to kind of sketch them out just to get a general sense of what the function would look like if it was a full equation instead of an inequality in one variable. But the idea is we're putting it on a number line. We're able to write it as an inequality in simplified form where just x is greater than or less than or between two values. So the key things to note is that we can solve these graphically or algebraically. Okay, and so all of these forms are potentially what we're wanting to be looking at. We always want to end up with it set equal in comparison to 0. Okay, and the reason that we're saying that a cannot be 0 means that if it was 0, we would then eliminate this term and it would become a linear inequality. So a can't be 0 in that general form. Okay, so when we're dealing with this, we can solve it graphically or algebraically, and we're going to have one variable. And the key thing to note is that we can have no values, one value, or an infinite number of values. Okay, so this idea of one value, like a specific number, is kind of an interesting idea. So we're going to kind of play around with how this all is going to look when we solve these. So this box over on the right-hand side just kind of gives you your stepwise kind of how to solve these. In terms of algebraically, this is exactly what you would want to do. So I'm not going to follow those steps for our first question. I'm going to look at it graphically just so that we get an idea of what exactly these pieces of information mean. So it says solve x squared minus 2x minus 3 is less than or equal to 0. What that means is that if I took this whole piece and I took all of its outputs, all of the outputs have to be less than 0. Now, output, when we think about a function, is our y value. So our y values, if I was rewriting this in like, kind of like in words, what I would say is that my function, or the output, of my function must be less than or equal to 0. So what does that mean? Well, if I tried to sketch this graph, the first thing that I always look for when I'm dealing with general form, and it's mentioned over here, is I want to look for my x-intercepts, which we are now going to call our critical points. The reason we call these critical points, we're going to see in a second when I kind of sketch this out. So first thing I'm going to do is solve for my x-intercepts. So how do I do that? Option 1 is the quadratic formula, but I like to not use that if I don't have to because it's a bit of a monster. So instead, I'm going to try and factor this first. And luckily, this particular quadratic is easily factored. So I factor it out, I've got my x-intercepts. Now I know a little bit more about my graph. So I'm going to be crossing at +3 and -1. From our second unit, we know that since our a value is positive, our graph is going to be opening upward, like this. And I've got a picture of what my graph actually looks like if this was a full function instead of an inequality. So this is saying, when we interpreted this, we said the outputs of the function must be less than or equal to 0. Well, where does that happen? Well, it happens between our two intercepts, where our parabola goes below the x-axis because all my y values down there are negative. This means that based on my graph, I can say that my solution, if I was to put it on a graph, is going to be from +3 to -1, inclusive. And I fill in those holes again because it can be equal to, and I'm going to shade the area between. So that would be my solution graphically. Algebraically, I would say that -1 is less than x, which is less than or equal to, which is less than or equal to +3. And so those would be my answers. So that's solving it graphically by analyzing what the statement that we are given actually means. This piece over here, algebraically, works a little bit differently. So dealing with this equation, we are going to follow those steps above, and so you have access to them on the same page. I might kind of scroll back and forth, so bear with me. First thing we would want to do is factor out our negative. So we've got x squared minus x minus 12 is less than 0. And I want to factor it because I still need to find my x-intercepts. No matter which strategy we're using, whether we're graphing it or algebraically solving for it, we need to factor our equation or use our quadratic formula to find our x-intercepts. The goal, step number 1, is to really find your intercepts. And so we get x minus 4, x plus 3. And those are going to be my intercepts. Those are what we call my critical points. Critical points are going to be +4 and -3. Now from here, what it says is we need to test the intervals to find the solution or use sign analysis to find the solution. So as we see in the graph from the previous question when we sketched our parabola, we've got a positive section, a negative section, and then a positive section. But we've got 3 potential segments that we need to check. So we're going to have that same scenario arising here. So we have, could x be less than -3? Could it be between our two intercepts? Or could it be above our larger intercept? So I like sign analysis. It just makes a lot of sense to me. So how that works is, oh, you know what? I'll talk you through test intervals and then I'll explain sign analysis. Test intervals means literally choose a value that fits each of these 3 scenarios and solve it. Okay, so option 1 is test intervals. So what that looks like is I'm going to plug in for less than -3, I'm going to choose -4. So I've got -4 minus 4 times negative 4 plus 3 is greater than 0. I want this statement to be true. So I've got negative 8 minus 1 is greater than 0. This is not true. Not true at all. The reason being, negative times the negative times the negative is a negative, which is not going to be bigger than 0. And then I'm going to check a value between these two. Whenever I find that it's available to me, I'm going to always use 0 because it just simplifies life. 0 minus 4, 0 plus 3 is less than 0. So we've got negative times negative 4 is positive 4. Oops, it's not less than 0. Oh, it is supposed to be less than 0. Sorry, I'm writing signs wrong. Greater than 0, greater than 0. So this one, oh my gosh, still writing it wrong. Less than 0, less than 0. This is negative, it is less than 0. This one is, section is good to go. It is the solution. It will satisfy our original inequality. Here we've got a negative times a negative is a positive, times a positive is still a positive. And so that is not going to be less than 0. So this interval is no good. Finally, we've got x is greater than 4. Well, what does that mean? Well, it could be 5. So let's check 5. 5 minus 4 and 5 plus 3 is greater than, not greater than, oh my gosh. I'm having a mental block here, people. Less than 0. 5 minus 4 is 1. That is positive. 5 plus 3 is 8. That's also positive. So I've got a negative times a positive, which is a negative. Negatives are, in fact, less than 0, which means that this scenario works. So that's test intervals. So as you saw, I didn't actually complete my calculations. That is the definition of the sign analysis piece. So I started with test intervals. I decided, okay, these are the 3 potential places where my answer could be true. And then I chose the values in there. And you're going to do that whether you're doing a test interval or sign analysis. You need to pick values and plug them in. It's just a matter of, do you actually solve all the way, or do you just analyze whether you would expect it to be positive or negative? The reason we're allowed to do just the sign analysis is because we're always comparing to 0. We always want 0 to be on our other side of the inequality. And so 0 makes the barrier between positive and negative. So that's why I was able to not complete the question in terms of solving for each side and getting an actual numerical value. So those are my critical points. These are my 2 intervals where it will be allowed. So option 1 is I write out my solution. So less than negative 3 or x is greater than 4. That's option 1 for how I express my solution. Option 2, and I recommend you do both. It's good practice. If this is 0, I'm going to positive 4. I'm going to have a hole there. And I'm going to shade this way. I've got negative 3. Again, it's a hole because it's not equal to, and I'm going to shade to the left. Make sure you have numbers on, or arrows on the ends of your number line, because they do go to infinity. So let's look at example 3. Okay, so we need 0 on that opposite side. In order to be able to do our sign analysis, in order to be able to determine our x-intercepts, everything requires that we get all our values on the left and set 0 on the opposite side. So we've got 2x squared minus 7x minus 12 is going to be greater than 0. So we try and factor this. So we've got, you can see it's a complex trinomial, so we're like, okay, well, 2 times 12 is 24. Factors of 24 are 1 and 24, 2 and 12, 3 and 8, 4, and 6. None of those are going to give me negative 7. So this is not factorable. What do we do if it's not factorable? We use our quadratic formula. So we're going to go over here and recall that x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. In this case, we are dealing with a, b, and c. Make sure we plug them in appropriately. So negative 7 plus or minus the square root of negative 7 squared. Please put that value in brackets to remember that that negative is included in our base, and it will eventually turn positive when we square it. 2 for A, negative 12 for C, and divided by 2 times 2. So we got 7 plus or minus the square root of 49 plus, because negative times negative is positive, 8 times 12 is 96, all divided by 4. And we could go one step further and go, okay, 7 plus or minus the square root of 3144 over 4, and that can be simplified even further. 7 plus or minus 12 over 4, which gives us a grand total of our critical points are going to be at 7 plus 12 is 19 divided by 4. 7 minus 12 is going to be negative 5. So those are my critical points. Those are my x-intercepts. They're everything that I'm going to base it on. Now again, I can do this graphically by thinking about, okay, what would my parabola look like? It would look something like this. I've got 2 defined intercepts. It needs to be greater than 0, so it's going to be defined on the outsides. Alternately, I could do my test intervals, and I'll do that again with example 4. Okay, but option 1, graphing. Option 2, we're going to do again is algebraically. Once I've plotted this and I've decided, okay, yes, those are absolutely true, they're going to be positive, opening up, everything is good. Again, I'm going to write my inequalities and I'm going to graph what this actually looks like when this statement is true. So x can be less than negative 5/4, or it can be greater than 19/4. So I can show that on there. I can also show this on my number line. Now 19/4 is going to be 4 and 3/4. So I'm going to need to go at least up to 5 on my number line and down to -2. I could even represent these with halves if I wanted. This is 0, -1, -2, 1, 2, 3, 4. I need to go a little farther. 5. Again, these are not equal to because my original question is not equal to either. So I've got from -5/4, which would be here, and going left, from +4 3/4 and going right is also a solution. So graphically, that's how I would represent the solution to that inequality. Second last example, we're going to do this again using the sort of sign analysis method. First thing we need to do, everything on one side. So I'm going to move everything onto the right this time just to switch things up. So I've got 2x² minus 5x minus 12. Now I had a similar setup here, except now I do actually have a difference that I can produce that 5. So I'm going to factor this, not use my quadratic formula. Okay, so break it up into its pieces. Don't forget to keep your sign appropriate. Factor out what you can from the first two terms. So this is x minus 4. Factor out what you can from the second two terms. X minus 4. Which means I'm left with x minus 4 and a 2x plus 3. Therefore, my critical points are going to be positive 4 and negative 3 halves. So I need to do sign analysis or interval testing. So x could be less than or equal to negative 3 halves. It could be between the two, or it could be greater than or equal to 4. So this time I'm not even going to do my test intervals. I'm not going to write down my value that I'm plugging in. I'm just going to mentally do it. This is something that you want to practice. So if I'm looking at less than negative 3 over 2, that my easiest value is probably going to be negative 2 that I'm going to work with. So negative 2 goes in for x. So if we think about it, negative 2 minus 4 is going to be negative 6. So that's a negative. I don't even care that it's 6. I just care that it's a negative. And I know that 0 needs to be greater than or equal to whatever ends up being on this side. Then I'm plugging in negative 2 for x in the second set of brackets. So 2 times negative 2 is negative 4, plus 3 is negative as well. Negative times a negative is a positive. This is not less than 0, so this interval is no good. Here we can use 0 because it's between our two. It's always very nice, which means we're going to be dealing with negative 4, so negative, and then positive 3. This means that we're going to be dealing with a negative value on the right-hand side. That is less than 0, so this interval is good to go. Finally, we're going to test over here, and you might have already figured it out based on what we've done with our graphic analysis. We've got positive 5 getting plugged in for 4, or for x. So we've got 5 minus 4 is a positive number. 2 times 5 is 10 plus 3, that's still going to be positive, which means this is all going to be positive. That is not true. Positive numbers are not less than 0. So in general, my solution is going to be negative 3 halves is less than or equal to x, which is less than or equal to 4. Graphically, how I would show this and show that what this inequality represents, I would this is 0. I'm dealing with negative a half and positive 4, and everything in between is fair game. So those would be my solutions. What about example 5? Example 5 says, if a baseball is thrown at an initial speed of 15 meters per second from a height of 2 meters above the ground, okay, so you might want to draw a picture for yourself. 15 meters per second, and it's 2 meters high. The inequality represents the time in seconds that the baseball is in flight. During what time interval is the baseball in flight? So it could look like this. And that, I'm already given my equation. So we're solving for t. And when does it make sense that it's above ground, so in flight? Well, we start with our negative 4.9 t squared plus 15t plus 2 is greater than 0. Given this information, I'm probably not going to try and factor this. I'm going to go straight to my quadratic equation, or my quadratic formula rather. So negative b plus or minus the square root of b squared minus 2 4ac divided by 2a. Again, a, b, c, that hasn't changed just because we're dealing with inequalities. So we're dealing with negative 15 plus or minus the square root of 15 squared minus 4 times negative 4.9 times positive 2, all divided by 2 times negative 4.9. I'm not going to simplify this on here because you guys have been using this quadratic formula for a while. I'm just going to punch it into my calculator. And so I get x can be, sorry, this shouldn't have been x at all, it should be t. My critical points are going to be negative 0.12798 and 3.189. Well, because I have my picture, I know, and because I have lived life long enough, we can't go backwards in time. So I know that technically my minimum is actually going to be 0. My maximum, and I know that it's actually in flight at 2 meters above, so it can't actually be 0 in terms of the time that the ball is in flight. The longest it's in flight for, then, is my 3.189 seconds, because this other value is negative. It's before time started, and so it doesn't count. I know that the interval is between these two values because I drew a diagram, so I don't even need to actually test my signs. Testing your signs is not a bad idea. You could always double check, but based on my diagram, my understanding of how physics works, and by using my eyeballs, I am able to figure this out, that it should be greater than 0, but less than or equal to 3. And it says we always have been going to the nearest tenth, so I'm going to go 3.2 seconds. So that's going to be my answer. Graphically, I would show this. I wouldn't even need a very big number line. This is 0. I'm going to start here. It's not going to be 0 seconds, and it can be just over 3 and everything in between. And so those would be my solutions. So there's practice in your workbook. Definitely give it a shot. Make sure you are super comfortable with the idea of quadratic inequalities, because that is what the assessment focuses on. The linear inequality piece of the first lesson was strictly a reminder or a refresher, an introduction into this concept. But quadratic inequalities is what we're focusing on.